There's an electric utility, and it has the following charges. There's a $5 base charge. It's like, okay, there's a fee for you just to even be hooked up to the service. Regardless of whether or not you use any electricity, you got to pay the base charge. But then, it depends on how much electricity you use. And they say, okay, it'll cost you 1 cent per kilowatt hour for the first 600 kilowatt hours, or less. So it's very inexpensive for the first little bit of electricity. You know, because people need to have some electricity. We shouldn't charge too much. We want to make sure that they are able to turn the lights on. If you move up and you're between 600 and 1200, so like the next 600, then you charge 0.02. Now, to be clear, you only charge 0.02 for anything over 600. So you still pay the 1 cent for the first 600, but now if you hit 601, that next one costs you 2 cents. And now if you're a heavy user, you're going to be charged 3 cents for anything over 1200. All right. So there's this tiered system going on. And the question, write a piecewise function for the electric bill based on the number of kilowatt hours used in the billing period. Now, we finished by talking about piecewise functions. So what is a piecewise function? We should remind ourselves. It says, hey, we have different behavior over different regions. And so what we'll do is we'll break up our description of our function for each one of these regions. We'll do them separately. So for us, there seems to be 3 natural candidates. These 3 right here. And they deal with how much energy gets used. So for the first part, what's the range of kilowatt hours that we're going to be interested in? And I guess I shouldn't have used the word range because the domain of the first 600. So this is if your kilowatt hours, I guess I use a capital W, is between 0 up to 600. How about the next one? Where is that going to be between? The next 600, so what does that translate into? Okay, 600 less than number of kilowatt hours, and up to 1200. And this last part? What does that correspond with? Yeah, we'd often say at 1200, the number of kilowatt hours is greater than 1200, but we could also say that 1200 is less than the number of kilowatt hours. And this can go all the way up. You could be having some large parties or something. Okay. So we're going to have to think about what happens in each one of our pieces. Now, we should come up with some convenient names. So there's the input, which is number of kilowatt hours. There's the output, which is your bill. So let's come up with names for these things. So I want symbols, preferably something short. What do you want to represent the number of kilowatt hours? There's not a wrong answer, it's just we're making a choice. So what do you want to have represent the number of kilowatt hours? We can use K. A lot of people use X, but why not? We can use K. Okay, so K will be the number of kilowatt hours used in our billing period. All right, and what do you want to call our function? In other words, the bill. What should we call that? Again, we need to pick a symbol. B? B for bill. We'll use a capital B. B. This is our bill that will be charged. Okay, so with this in mind, so now we're going to look at our bill as a function of kilowatt hours. And so we say it's going to be one of three things. And we're going to break it up according to these portions here. So there's going to be if our input, number of kilowatt hours, is between 0 and 600. If our input is bigger than 600, but less than or equal to 1200. And if our input is bigger than 1200. All right, so we have to decide what's going on in each one of those. So let's start with the first one. We're between 0 and 600. How do we figure out our bill? We're between 0 and 600. What can affect the bill? We have two things. We have the base charge, and we have the number of kilowatt hours that we use that will increase our bill. So our base charge is always there. So how do we put that into our formula? Yeah, there's going to be a plus 5. So I'm going to go ahead and put that at the beginning, 5 plus. And then, so the 5 is always fixed. It doesn't matter how many kilowatt hours you use, there's the 5. Next up, there's the varying part, the 1 cent per kilowatt hours. And so that depends on how many kilowatt hours we use. What comes here? 0.01 K. So 5 plus 0.01 K. That's our bill. If we're below 600. Now, we use a little bit more. Now we have to sort of have three things coming into play. We've got the $5 base charge. We've used up the first 600 kilowatt hours. How much will the first 600 kilowatt hours run us? We're using 600 kilowatt hours. It's costing us 1 cent for each one of those kilowatt hours. How much will the first 600 kilowatt hours run us? $6. So we have the base. We add those first 600 hours. Now we could just write that as an 11, but I'm just separating this so we can see where it's coming. And then we have the additional kilowatt hours. So we're between 600 and 1200. How much will that cost us? Is it 0.02 K? Okay, it's not 0.02 K, but you're on the right ballpark, right? It's 0.02 times the number of kilowatt hours, but we already got charged for the first 600. So we can't be charged again for those 600 kilowatt hours. So now we can only need to be charged for the kilowatt hours past 600. So how many kilowatt hours do we have left to be charged? We've already paid the bill for 600 of them. We've used K of them. How much is left to be charged? 600. Then there's an additional K of them. All right, so there's a total of k of them, right? The 600 we've already been charged for. How much is left for us to be charged? The answer? Well, we know it costs us 2 cents, but we're going to multiply by k minus 600. Because we've already paid for 600 of them right here. So we're not going to be charged twice. We just have to pay a higher rate for all the ones over 600. Does that make sense? Okay, so now the third part. I did a very terrible job of aligning there, but we'll do better on on this final one. Okay, so now we've used a lot of electricity. What goes into our bill? We have the base charge. So that's 5. What else do we have? Yeah, we got the first 600 that we need to pay for, and that's just going to cost us 6. Then what? $12, because the next 600 cost us 2 cents per hour. So that's plus 12. Now we could combine all these together and say 23. And then we have to pay for anything left beyond that. So we've already paid for the first 1,200 kilowatt hours. That shows up in the 6 and the 12. So now we have to pay for anything over 1,200. And we're charged 3 cents per hour. So what gets written down? $0.03, because that's the rate, times what goes here? K minus 1,200. Now we can try to put these all together. 5 plus 0.01 K if we're between 0 and 600. 11 plus 0.02 K. Oh, I should have actually done some fun stuff here. Never mind, I won't go this way. You could have multiplied this out and rearranged things. But okay. All right, any questions? Okay. All right, so that's an example of piecewise. And the idea of piecewise is different things happen over different intervals. So it's not an unusual thing to see. Okay, one other thing. Let's do a practice before we get to today. So we practiced and talked about the idea of transforming graphs. So below is a graph having the form y equals a times x minus c quantity squared plus b. And it's asking us to determine the values of A, B, and C. In particular, what's gone on here, well, essentially, you said, oh, you're starting with a quadratic, or parabola, y equals x squared, and then you're doing a horizontal shift, that's what the C does, a vertical shift, that's what the B does, and a stretching. That's what the A does. So, we need to figure out what's going on. Now, I like to say, look, this parabola has a very nice point here at 0, 0. And we'll give that a name today. So, can we figure out where this point went? Where did it go? Well, it went down to where it's been marked. So it's like you've moved things. So the question, how much did we move? How much did we move in the horizontal direction? 2. And it's a positive 2. So that deals, the horizontal deals with inputs. What does that say about your value of C? And here we have to be ever so careful. Notice that there's a minus sign. It says that, oh, horizontal shift was 2, so you want an x minus 2. So you want x minus whatever your shift is. What's our vertical shift? -3. Where does that go? Goes to the B. So the shifting is the plus or minus. Because it's on the outside of the square, that says I'm dealing with outputs. So that's why we think of it as a vertical effect. Okay, so good news. We figured out 2 of our 3 entries. How do we figure out the A? What can we do? What can we do? Well, if I was on the parabola, if I came over to 1, what would the output be? Input is 1, output is? If x equals 1, y equals 1. So it should be that if I move 1 over, if I did no stretching, I should just move up by 1. But notice here, I move 1 over. How far have I moved up? We moved up by 4, right? Because I went from -3 to +1. The difference, 1 subtract -3, says 4. So originally, you should only have moved 1 over and 1 up. But now we moved 1 over, and now we've gone 4 up. So we've had to have stretched it to have that happen. So the question, what is A? It's 4. Yes, it's 4. Is it +4 or -4? And how can we tell if it was positive or negative? It's +4. If it was -4, what would need to be happening with our picture? Yeah, it would be like an upside down. Here, positive, the bowl holds water. Negative, the bowl does not hold the water. So this is 4. Now, if you don't like that explanation, you could have said, well, I at least know how to shift. And then I can say, I have some points given here, so I could just plug in. Pick a point, doesn't matter. Suppose I plug in here. So I'm told y is 1. That's equal to A times 3 minus 2 quantity squared minus 3, which becomes 1 equals A minus 3, or just adding 3 to both sides, A equals 4. So that's another way you could have done it. But all right. And the moral is, and we're going to talk about this, every parabola can be written in this form. All right. So, what's today? We're going to talk about quadratic equations. We'll talk about various shapes of it, x-intercepts, y-intercepts, the vertex, talk about domain and range, do graphing, and hopefully some applications. So what's a quadratic? Basically, if you look like ax squared plus bx plus c. Polynomial of degree 2. That's a quadratic. And every quadratic can be written as a times x minus h squared plus k. We call this vertex form. And we'll talk about what the vertex means in a second. Of course, I should give a quote. I don't know who came up with this, but this is something I learned from my professor when I was a student at your age. And I still remember it. It was good advice. And here it is. Try something. If that doesn't work, try something else. But never give up. I think one of the biggest challenges people have is that they don't even start with the first thing. They're afraid to try something because they might be wrong. You can't make progress if you're afraid of being wrong. Try something. You might fail. Most things do the first time you try something. But you learn. And you try something else. And as long as you keep at it, you'll get there. All right. With everything we've done, a lot of today will be very straightforward. And let's see, I think this is essentially the lecture for today, is this slide. But then we have to do practice. So quadratic functions. I already said it's a second degree polynomial, ax squared plus bx plus c. You have to have the coefficient of x squared not be 0. What happens if the coefficient of x squared is 0? Well, then that term goes away, and what do you get? bx plus c, which is y equals bx plus c, which is, it looks like slope-intercept. It's a line. Yeah. Okay. Now, what are things that we might want to do? Well, we might want to know the y-intercept. And the y-intercept of functions is the easy one. Because how do you find the y-intercept? You say, where do we hit the y-axis? You hit the y-axis when x equals 0. So how do we find it? You plug in x equals 0. And if you plug in 0 to your function, you get 0 times a and 0 times b. Hard to recover from multiplying by 0. And you get c. So that constant on the end, that's your y-intercept. How do you find x-intercepts? Well, x-intercepts, that's where you hit the x-axis. Now, you describe the x-axis by saying y equals 0. Okay. So now you put y equals 0. The output gets set equal to 0. 0 equals ax squared plus bx plus c. And then we're like, whoa, we talked about this. This is like solving a quadratic equation because it's solving a quadratic equation. And we can do things like factoring. We can also do things like the quadratic formula. So you have your x is negative b plus or minus the square root of b squared minus 4ac over 2a, the sort of quadratic formula. Now, the behavior for the intercepts comes down to what's inside the square root. b squared minus 4ac is negative. That means we don't hit the axis at all. So it's a parabola that's either completely above or completely below. And that's perfectly possible. It can happen. If b squared minus 4ac is 0, we hit the axis. We have the x-intercept exactly once. And in the language of vertex, which we haven't talked about yet, that means the vertex is on the x-axis. And we'll talk about what the vertex means in a moment. If b squared minus 4ac is positive, you get 2 x-intercepts. All right. Now, you can rewrite ax squared plus bx plus c into a times x minus h squared plus k, and you do that by completing the square. So we'll do an example of complete the square in a moment on the next problem. But essentially it says factor the a out of the first 2 terms, and then complete the square of what you have. Now, in this form, you have a special pair of numbers, h and k. If you think back to the problem we did, those are your vertical and horizontal shifts. So what it says is you're taking what was at 0, 0, and you're shifting it over to x equals h and y equals k. So this point, hk, that's what we call the vertex. So essentially it's the very top or the very bottom. I mentioned before, this is an example where you never hit the x-axis. So if A is positive, we open up. A is negative, we open down. Once we know where the vertex is, that helps us answer questions. Particularly helps us answer questions about what kind of outputs we have. If A is negative, the highest we can get is at the vertex, and we can get anything below. If A is positive, the lowest we can get is the vertex, and we can get anything above. So we can find the range. So if we can find the vertex, then we can find the range. All right. This is the lecture. Everything else after this is practice. Any questions? All right. Good. Well, let's try an example. Okay. So here we have a nice, lovely quadratic formula. Negative 3x squared plus 6x plus 24. And we want to do the following. We want to find y-intercepts, x-intercepts if there are any. There may not be. Write it in vertex form. Find the vertex. Find the domain. Give a sketch. All right. Now, there are some things that we get automatically. Without doing any work, can you tell me, once we get to our sketch, will this be opening up or opening down? And how do you know? Down. How do you know? Yeah, the coefficient of the x squared. That dominates the behavior. You see, it's negative, going down. So we know it's going to be a downward facing parabola. Okay, let's start at the first one. The y-intercept. Do we know what the y-intercept is? What is it? It's 24. So in this format, we can just see the answer. In general, if in doubt, plug in 0. All right, so y-intercept, no problem. Okay, now let's go to x-intercepts. So x-intercept says, hey, set the output equal to 0. So we can do that and solve for x. And we can do this in any way that you want. So, what would you like to do? Would you like to attempt to factor? Would you like to use the quadratic formula? Attempt to factor? Okay, is there anything we can do before we attempt to factor to make our lives a little bit easier? Look for common factors, right? 3, 6, 24. They're all multiples of 3. And I'm going to pull out the negative as was suggested because I like to have what's in front of the x squared be positive. Always look on the bright side of life. All right, so we pull a negative 3 out. It becomes x squared minus 2x minus 8. Okay, can we factor x squared minus 2x minus 8? It does look a little bit more straightforward than what we had before. We need two things that would multiply together to give us 8. Specifically negative 8, I should say. But would add together to give us negative 2. So someone has suggested negative 4 and positive 2. Let's see if that works. X squared, good. 2x minus 4x is minus 2x. And minus 4 times 2 is negative 8. All right, so good. And we use our fun fact. If 0 is the product of things, that means one of these things had to be 0. By the way, it's definitely not the negative 3. That's not 0. If x minus 4 equals 0, What does that tell us about x? It tells us x equals 4. X plus 2 equals 0 tells us x is negative 2. So there are intercepts here. So at negative 2 and at positive 4. All right, so we have that information. Write it in vertex form. So now we're going to go through and do completing the square. So we have our f of x equals negative 3x squared plus 6x plus 24. Okay, so what's our process to write in vertex form? I'll just give some useful steps, at least what I find useful. Factor the a out of the first two terms. And leave a gap. Okay, so what I mean by that? So negative 3, that's what's attached to the x squared. That's what I'm calling the a. I'm going to factor it out of the first two terms. So that you get x squared and minus 2x. It's the same as what we were doing up here when we factored negative 3 out. Then I'm going to leave a nice big gap. Now, secretly what we're planning to do is we're planning to add 0. Because it's one of the fun facts that if you add 0, it's the same thing that you just had. It's just a different way of writing it. And you're like, okay, so let's just add 0. But we say, no. It's not just add 0. It's add a really well-chosen 0. We must choose, but choose wisely. Okay, so now that gets us to our next step, which is complete the square. And then add 0. So when I take complete the square, now just focus on the x squared minus 2x. What would I need to add to x squared minus 2x to make it a perfect square? So the procedure is take what's in front of the x, divide by 2. Negative 2 divided by 2? Negative 1. Square that. You get 1. So that's what you need to add. So if I add 1, then this part becomes x minus 1 squared. It becomes a perfect square. So divide by 2 and add the square. But I can't just add 1 because that changes the function. That's where this minus 1 comes into play. So if I add 1 and then immediately subtract 1, I haven't changed my function. Still the same function. But now we're in our home stretch. Because what do we have? We have our negative 3. We can now distribute it into the first part. It's x minus 1 squared. Then we have negative 3 times negative 1. Makes a positive 3. And add 24. Or this becomes negative 3 x minus 1 squared plus 27. All right. So that's the vertex form. Okay, so that's been done. From vertex form, we can read off the vertex of the parabola. Where is our vertex? It's a point, so something comma something. X coordinate is 1. It's this piece. X minus what? What's the y coordinate? 27. So what's being added on the end? So 1 comma 27. Yes?
Where'd you get the 3 from?
So this first part right here became your x minus 1 squared. You still had this minus 1. So minus 3 times minus 1 is where you get the plus 3.
And then when you made the x minus 1 like squared, you still use the 1.
Yeah, so we could have written another step. So this is minus 3 times x minus 1 squared minus 1 plus 24. And then you're just distributing the minus 3 through. All right. The domain. What's the domain of a quadratic function? What inputs are you allowed to put in? Yeah, the domain for a quadratic is all x. There's no problems. The range you have to think about. What's the range? This will tie back to our vertex. So the vertex will be either the top or the bottom, depending upon whether we open up or down. So, what's our range? So do we open up or down? So we've already said this, since this is negative, we open down. So before we answer the range, we can even do a quick sketch. So we can do the following. We just mark here. We go up to 127. So that's a point. Picture may not be to scale. So there's 127. And then we open down. This point, by the way, is 24. That's where we hit the y-axis. Over here is negative 2. Over here is positive 4. Okay, so what's the range? What outputs can we get? Up to 27. We can't get anything above 27, but we can get everything below 27. So our output is anything less than or equal to 27. That's our range. One quick comment. You get symmetry. In other words, if you were to go down through the vertex and cut it, it's going to be a mirrored image across that line of symmetry. So one of the things that tells you is if you look at how far, well, if you look between negative 2 and 4, what's halfway between negative 2 and 4? It's 1. So the x-coordinate of your vertex will always be between your x-intercepts. Halfway between, exactly halfway in between. If your vertex is not halfway in between your x-intercepts, mistakes were made. And that's okay. That means we can correct our mistakes. Woohoo! Correct the mistakes. Correct the mistakes. Any questions? All right. Let's do a word problem. Marketing research has shown that the price-demand function, so that means the price they can sell it at, depending upon how many units are made to be sold. So if you don't make very many units, it's a rare item, you can charge more. But if there's a lot of units, people are going to be like, oh, this is common. I don't want to pay a lot if there's so many of them out there. You know, it loses its prestige. So the price you can charge goes down. You know, it's like very fancy cars. Very expensive cars, they make very few of them, and they don't want to make many of them because they're so few, they become a status symbol. So that's why you get to charge more. But mass-produced cars, they're not seen as a status symbol, you get to be charged less. All right, so our price is 75 minus 3x. All right. How many units should be produced, and at what price should they be sold to maximize the revenue? Now we're going to make an assumption that we're going to sell everything that we make. I like that assumption. It's a good business assumption. Okay. Now, this problem doesn't seem quite right for us. What is this not? This is not a quadratic. So you're like, why are we talking about it here? Okay, so let's think about this. We want to maximize revenue. Okay, that means make it big. This function is not the revenue. It's the price we get to charge. How do you find revenue? Channel your inner economist. Econ 101, first day in class. Oh, sorry, Econ 1010. We have to change the name because we've added an extra digit. How do you figure revenue? If I know how much it costs, how much I get to sell it at, and that's the answer, and I know how many things I sell, and that is I sell all of them, how do you find revenue? Cost times quantity. Now, how much did you get to charge? How many did you sell? So our revenue function, we have to write it down. So our revenue, so we'll use R for revenue because we want to make sure we can keep track of what things represent. We can choose absolutely completely random symbols, but that makes things harder to keep track of. We want to understand what we're doing. So we use R. So our revenue is going to be our price that we can charge. So this is the price times how many you sell. This is quantity. Price times quantity. If you like, we can multiply this out. This is 75x minus 3x squared. Or if we write it in the way that we've been talking about, minus 3x squared plus 75x. All right, so that's our revenue. That's how much money we're going to make depending upon how many units we sell. So, we're asked to maximize the revenue. Now, if we go back to our lecture slide, way back from a few minutes ago, there was a word we kind of glossed over, which is the maximum and the minimum. If we have a parabola that opens down, the maximum occurs at the vertex. If we have a parabola that opens up, the minimum occurs at the vertex. So, when it's asking about maximizing, it says, this is like, where's the vertex? So that's the question we're after. So we need to find the vertex. How can we do it? Well, let's just do the procedure we've talked about. Let's go through it and we'll factor the -3 out. X squared minus 25x. Leave ourselves a gap. Okay, -25. This will be fun. -25 divided by 2 is 12.5 or 25 halves. And then we're going to square that. So we're going to add 25 halves squared. If we add it, we can subtract 25 halves squared. And so this becomes -3 times x minus 25 halves, quantity squared. So that's completing the square. And then there's this extra term here, minus 25 halves, quantity squared. And if you distribute the -3 through, you get -3 times x minus 25 halves, quantity squared, then plus 3 times 25 halves, quantity squared. Okay, so that's completing the square, writing it in vertex form. Now, with this, we can read off our answers. Well, almost. Question 1. How many units should be produced? How do we figure that? Yeah, so this is the x part of your vertex. And in this case, it says what? Well, 25 halves. Now, that might sound like a weird number. Sometimes they use X for thousands of units or millions of units. But let's just say, okay, whatever. We'll let the accountants figure out the 25 halves. So that's the answer. 25 halves. Now, quick question, and then we're done. And at what price should they be sold? How do you get the information about what price we should sell them at, given we know how many units we should produce? Put it into the price function. So we should be shooting to price it 25 halves. So, price it at x equals 25 halves. So that's 75 minus 3 times 25 halves, and then whatever that number that turns out to be.